So I welcome all of you after the break. So let me share my screen. So am I audible?
Yes.
Yeah.
Yes, sir. Yes.
Thank you very much. So before the break, we have discussed about uh, how to maximize the revenue using two algorithms. One of the base algorithm is RSU based resource scheduling. Another we have seen resource revenue based service management, that is RBSM. So we'll see another problem in the area of fog, where IoT devices are also there. IoT devices are inbuilt with our smart vehicle, and these fog nodes are again connected to the cloud. So it is integration of again IoT, fog and cloud. So we consider here there is a network. Just assume that a particular city and a location of a particular city, which we represent here as a area, that is A. And in that area, suppose we have put some kind of some fog nodes in different locations. Let's say the number of fog nodes is F. For example, if you see this picture, here you can see there is 4 fog nodes. One is fog node 1, another is fog node 2, another is fog node 3, another is fog node 4. So if you consider this is a location of a particular city, we consider that city is A, in which we divide the city area into different zones. So normally in network point of view, these zones are represented in a hexagonal shape, but easy representation purpose, we consider it is in the form of circle. So each fog node is having a particular range, whether it is a fog node 1, fog node 2, fog node 3 or 4, they have a particular range. Generally, these fog nodes, we consider their coverage region is same. Like for example, coverage region of a fog node is 100 meter. Then we assume that every fog node is a coverage range is 100 meter. But you can take heterogeneous fog nodes also, where a powerful fog node may be covering more than 100 meter. Right? That is also possible. But for this particular example, we consider the range is 100 meter. Okay. Irrespective of that, if it is 100 meter or 200 meter, but the range is same for all the fog nodes. And we also assume that a particular fog node area is overlapping with the area of another fog node. Like here you can see there is a fog node FN1, and there is another fog node FN4, and the area of fog node 1 is overlapping with the area of fog node 4. Okay, so we consider the overlap region. Okay, there are some vehicles that are available in the non-overlap region, but we assume that at least some vehicles is available in the overlap region of the communication range of two fog nodes. Like another case you can see here. So this is the coverage range of FN3, and this is the coverage range of FN4. So this particular vehicle can get services from FN4, or it can get the services from FN3, because it is available in the overlap communication range of fog node 3 and fog node 4. So this is a typical illustration in which we consider 4 fog nodes, and I think we have taken 10 different vehicle. This is vehicle 1, then vehicle 2, you can see vehicle 3, vehicle 4, vehicle 5, vehicle 6, vehicle 7, vehicle 8, vehicle 9, and vehicle 10. So out of these 10 vehicles, B1 to B10, some vehicles are in the overlap region, and some vehicles are also present in the non-overlap region. Right? For example, you talk about vehicle B8 or B9 or B10 or B7. They are under a particular fog node. They are not in between two different fog nodes, because they are available in the non-overlap area at a particular time instance. But if the time instance change, So then it may happen that this vehicle which is moving here, it may be available in this particular region. Okay, but we take a snapshot. That's why in that particular period of time, that vehicle is in the non-overlap region. And a particular fog node provides services to set of vehicles. This fog node is not only providing services to vehicle 9, it can also provide services to vehicle 6 and also to vehicle V3. But together V9, V6 and V3, they should not exceed the maximum capacity. So assume that this vehicle is having something, some rough calculation or informal case, I can say it is 100. It is taking, let's say, 20 resources. It is taking, let's say, 70 resources. It is taking 10 resources. So 70, 20 and 10, it is 100. So this FN3 can provide the resources, right? But if it is exceeding, for example, let it be instead of 10, I am saying 15. So it is not possible to provide services to all the 3 vehicles, right? You can provide V6, V9, or you can provide V9 and V3. Okay. So one of the vehicle will not going to get the service. That's why a fog node provides services to a set of vehicles and reaching its communication rate at a particular time slot we consider that is tricky. So the main challenging problem is that how to provide the services to maximum vehicles. Assume that there is approach X in which out of 10 vehicles we are able to provide 7. 7 vehicles are getting services out of 10. But you have developed a policy, let's say X dash, where you got out 8 out of 10. Then obviously your approach is better in comparison to others' approach. Now, you can notice in this particular picture, I am also represented some numeric value, which is a 3-digit value, which we call as resource block. Okay, we assume that that is a resource block. Okay, and if you want to know about resource block is defined using this particular equation. So if I take resource block RB IK, so you can see we are writing subscript as I and superscript as K. So subscript represent the fog node, the subscript represent the fog node, and superscript represent the vehicle. That means if I write RB, I and K here, what it indicates? Total number of resource block required for kth vehicle with a data rate dk from the ith fog node. Okay, I represent the fog node, K represent the vehicle, and D to the power K is represent the data rate of kth vehicle. So when kth vehicle is present in the coverage region of ith fog node, if a particular fog node I am taking FNI, if a vehicle is available in its region, then only the resource block you can calculate. So resource block is calculated as ceiling of 1 by B into log base to 1 plus SIK into DK. DK I already told you, it is the data rate. B is bandwidth and SI is the, and again SI we are using 2 variable. I is considered as a fog node, K is considered as a vehicle. So SIK represent signal strength between ith fog node and kth vehicle. Okay. So if you understand this one, this mathematical equation, it's type. Otherwise, you just simply take this as a 3-digit number. We have generated it randomly. So this much resource block, okay, is required to connect to that particular fog. Another important thing is it is a type of simulation. So you have to depend upon some type of distribution. And we know we have different type of distribution like normal distribution, uniform distribution, we have Poisson distribution, we have binomial distribution. So there are different type of distributions we have. So here we have taken the Poisson distribution. So this distribution is actually used for the arrival rate and departure rate of the vehicle to and from the network with mean value is lambda or mu. That means arrival rate we have taken as lambda, departure rate we have taken as mu. Arrival rate means a vehicle is arriving in the network. Departure rate means a vehicle is leaving the network. So if you consider this is a particular network, in a city area, we consider this particular network. So how many vehicles are entering to a particular network and how many vehicles are leaving from that particular network. So arrival is represented as lambda and departure is represented as mu. Okay. For example, if you consider NITW campus, okay, assume that this is our campus. Okay. Suppose we observe that let's say there are 50 vehicles entering to our campus at a particular time instance, and let's say 30 vehicles are leaving the network. That means my mean arrival rate is I can consider as lambda, which is 50, and mean departure rate I can consider mu is equal to 30. Okay, so here I am showing a situation where lambda is greater than mu. 50 vehicles are arriving in the network. At the same time, 30 vehicles are leaving the network. Right? If you take a particular area, any vehicle can enter, any vehicle can go. Right? Another situation you can say where I can say, let's say 50 vehicles are entering the network and 50 vehicles are also leaving the network. So I can say lambda is equal to mu. Okay. It is an ideal situation. The number of vehicles entering to a network and number of vehicles leaving the network is same. Another situation you can say, like a number of vehicles entering the network, let's say lambda is equal to 20, but number of vehicles leaving in the network is quite more. It's 30. So in the third situation where lambda is less than the mu. So this situation can be possible, right? If 30 number of vehicles are there inside the network. Normally, arrival rate may be considered as more than the departure rate. But if I'm considering departure rate is more than the arrival rate, this situation, we have to assume that that many number of vehicles are available inside the network. Then only they can depart. Otherwise, it is not possible. If the entire network is empty, if now no vehicle is there, then it is not possible to get this particular case. So we consider all these three cases in a particular network. Okay. So here we are seeing 4 different fog nodes and 10 vehicles. So you can see that how many vehicles are entering and how many vehicles are leaving. Okay. For example, if you see, let's say fog node 2. In fog node 2, how many vehicles are there? In its coverage range, 4. Let's say these 2 vehicles are leaving and these 2 vehicles are, let's say now it is available in this range, but after some time it is going to leave. This is also, these 2 vehicles are also going to leave. Means all the 4 vehicles are going outside the network. Okay. So in this case, you can say leaving rate is more, right? Lambda is if it is arrival rate is less than the departure rate. So it is possible because 4 vehicles are inside the network, right? Similarly, if you consider fog node 3, okay, in this case, you can see there is 2 vehicle entering to the network where another vehicle is departing the network. So I can say lambda is greater than mu. That is 2 is greater than 1. Number of vehicles leaving is less in comparison to number of vehicles entering to the network. Similarly, what I can say, if I take another situation here. Here 1 vehicle is entering to the network and 3 vehicles are departing the network. So lambda is less than mu. Similarly, if you take the first case, in this case, this vehicle is entering to the network, this is also entering the network, and this vehicle is leaving the network. So what we can say, number of vehicles arriving in the network is greater than the number of vehicles departing the network. So like that, we can create several situations. Okay, we can create several situations in this particular scenario for the simulation purpose. Okay, this is too mathematical. If you have not understood, it's fine. Now you can understand through examples. So what is the problem? The problem is that over a period of time, generally if you see our working hours time, the number of vehicles connecting to the network is periodically increasing. Like you see in the daytime, we have heavy traffic. But if you see the early morning time or late evening time, the number of vehicles are reduced, right? So, but if the number of vehicles are increasing, definitely they require resources, more resources. So it can adjust the capacity of the fog node, because every fog node, as I said, it is having a limited power. It is not having unlimited capacity. Everybody has some restrictions, right? So it is difficult for a fog nodes to provide services to all the vehicles. So in that case, what happens? A fog node has to decide which vehicle it is going to select to vehicle it has to select to provide the services, because we cannot provide services to everyone due to our limited resource constraints. So in order to make space for new incoming vehicles in the fog node, you have to ensure that adequate resources is there. If inadequate resource is there, then definitely new vehicles are not going to get the service. Now, one of the solution we can think that services of the vehicles are migrated between pairs of fog node, right? One of the solution we can suggest that if some vehicles are available in the overlapped region, so they can be exchanged between one fog node to another fog node. Exchange means it can be migrated, right? So if two vehicles are there between FN1 and FN2, so if first vehicle is getting service from FN1, second vehicle is getting from FN2, then let's say they are migrated. Now first vehicle gets services from second fog node, and second vehicle get services from the first node. That is called as migration, right? So the services of the vehicles are migrated between pairs of fog node without increasing the number of resource blocks. We have to ensure that the number of resource blocks requirements would not be increased, right? Like if I take two vehicle, let it be vehicle 1 and vehicle 2, and this is my fog node 1. Okay, so it is getting service from here, and it is getting service from this one FN2, right? Which I said. Now I am showing in graphically, right? So I can do it in a situation like this where FN1 is connected to this one, FN2 is connected to this one. That we can do, right? So this is called as a migration. If I take V1, V2, so you can do this migration without increasing the number of resource block. Suppose resource block requirement is here 500 and it is reduced to 480, then we are going to accept this migration. But if it is increased to 550, assume that it is increased to 550, so we are not going to accept this migration. Okay, so in this case, in this way, we are going to connect with the network, right? So the main objective is here is to maximizing the resource block reduction. Our objective is resource block reduction. Resource block reduction means it is a minimization problem. Okay, and that you have to maximize, right? Here 500 to 550 it is increasing. That's why we are not accepting the solution. But if 500 is reduced to 480, we are accepting the solution because resource block is reduced. So if you can maximize the resource block reduction, so definitely we can provide services to many vehicles. So we consider some of the performance matrices here, like service capability need to be maximized. Okay, we measure the performance of a network system, IoT, fog, and cloud-based system, where service capability need to be maximized, serviceability need to maximize, availability need to maximize, throughput also need to maximize, and utilization efficiency should be maximized. Right. So if it is maximized, then only you can get you can provide services to the new upcoming vehicles, right? So let us try to understand what is the meaning of these performance metrics in the next slide. So what is service capability? Service capability is nothing but the ratio between remaining resources and total number of resources in a network. For example, total number of resources in a network is 100 and remaining resource is 30. Right? That means you have it is 0.3. Right? That is service capability is 0.3. If remaining resource is more, let's say 90 by 100. So it is 0.9. So if the value is close to 1, okay, if the value is close to 1, it indicates that remaining resource is more. If the value is close to 0, that indicates that the remaining resource is less, right? Like you can see remaining resource is less, that's why it is close to 0. Remaining resource is more, that's why more number of resources are available. So you have to calculate this ratio. And our objective is to maximize. If more resources becomes available, then in a network, if more vehicles are available, we can provide the services. So that is one of the parameter. Another parameter is that is called as network serviceability. So it is percentage of vehicles getting served with desired requirement in a network. For example, you want to watch a YouTube video, okay, with 1080p. That is your desired requirement. But your internet is not good. As your internet is not good, right? You are getting, let's say, the video with 420p. Sorry, 480p. Whatever maybe. Okay. So your desired requirement is 1080p. So if somebody provides the video with 1080p, your requirement is fulfilled. Right. But sometimes due to internet issues, or you can say bandwidth issues, we are not going to provide it this one, but we are going to provide in this one. And you say it's okay, it is not good, video is not good, but still it is manageable. So serviceability says that how many vehicles out of, if you consider in a network 100 vehicles, what is the percentage of vehicles getting the services is desired requirement. While the network's availability says that at least they are getting services. Okay, at least they are getting services with minimum requirement. One is desired requirement, another is minimum requirement. Okay, still, as I said, my requirement is 1080p, but I am manageable with 480p. So my minimum requirement is satisfied, but desired requirement is not satisfied. So you can say sometimes in network we say quality of experience. Quality of experience is not satisfied if you are not providing in 1080p. But your requirement, minimum requirement is fulfilled. So in general, in network term, if we consider, let's say 0.5 to 2 MB, so we consider 0.5 is the minimum requirement, and any value which is greater than 0.5 and less than equal to 2, we consider that as desired requirement. So we consider that 2 as a performance matrix here. Now, next there is another one that is called network throughput. So network throughput is obtained using vehicles achievable rates at a different time slot from different fog node. So throughput means it is performance, right? How much vehicles are getting the services, right? In a particular time slot, right? Let's say time slot t is equal to one vehicle got service. Take time is equal to two vehicles are getting services. We'll try to accommodate more vehicles. So network throughput is directly proportional to the time fraction allocated to the vehicles getting services. So we have seen also that if maximum vehicles are getting services in every time slot, then throughput is increases. And the last performance matrix is that resource utilization efficiency. Resource utilization we are calculating based on our resource blocks. So it is the percentage of occupied resource block in a network. Suppose I have 1000 resource blocks, out of which let's say 90 resource block is filled. Okay, so I can say 0.09. Okay, if say 100 is there, 100 resource block is filled, then it is 0.1. So resource utilization efficiency we calculate based on the percentage of occupied resource block in a network. Okay, if you have let's say low resource utilization, although it is not good, but upcoming vehicles can get the services. So these are the 5 parameters that we use to evaluate the performance of a network. Okay, now in order to solve this problem, again I am repeating the problem here. Our problem is to maximizing the resource block reduction. And the process which we adopt is that migration between pairs of fog nodes. We have to migrate without increasing the number of resource blocks. That is our objective, right? So let us see how we are going to do it. So we'll discuss 4 algorithms. One is obviously hybrid algorithm. That's why I told you 3 at the beginning. One algorithm is called as dynamic resource orchestration algorithm. Second is signal aware algorithm. Then people have come up with combining DRO with SA algorithm. Fourth is our algorithm, that is DRM algorithm. And fifth one also we'll see one of the base algorithm, that is RO. So basically, I told you these 3, but there is a baseline algorithm and this is a hybrid algorithm. So these 5 algorithms we will discuss in this session so that you can compare, you can say, one technique with any other technique, right? And we'll see which one is performing better in a particular situation. So if you go for this first algorithm, that is DRO algorithm. DRO algorithm uses maximum weight matching. You can see here, like if a network is given to you, you have to convert that network into a graph. All of us know graph is represented in the form of set of vertex and set of edges. Vertex is nothing but here the fog nodes. Edges is nothing but between 2 fog nodes. Okay, Fn to Fn. Okay, one fog node to another fog node, we put a edge. And we represent in the graph where edge represent if you do migration. For example, I am taking a fog node 1 and I am taking fog node 2 and I am putting an edge here. That is a directional edge, not a indirect edge, not a undirected edge, is a directed edge. So if I am write 120, what it indicates? If I am going to migrate Fn1 to Fn2, or you can do also Fn2 to Fn1. Okay. If you do Fn1 to Fn2 or Fn2 to Fn1 at a particular time instance, let's say number of resource block you are reducing, it is 120. Right. So that value, that is nothing but the weight of the edge. Right. If you exchange this one, we are going to reduce 120 number of resource blocks. Okay, let us see DRO algorithm. So here I am showing you a service migration using DRO algorithm. So I'll show you in each and every case through an example, before migration case and after migration case, so that you can compare which one is providing you better solution. For example, if you take, there is 4 fog nodes, means you have to compare Fn1, you have to compare Fn1 with Fn2. Okay, you can do migration between fog node 1 and fog node 2. Similarly, you can do migration with Fn1 with Fn3. You can also do migration with Fn. Fn1 is not directly connected to Fn1 can connect it to Fn4 also, but I think Fn1 is not connected to Fn3, so this case never arises. Right? You can see this is the coverage range of Fn1. This is the coverage range of Fn3. So there is no overlap. So this case is not arising here. Okay, but Fn1 is overlapping with Fn2 and Fn1 is also overlapping with Fn4. These 2 cases exist. Similarly, if we talk about Fn2, Fn2 is overlapped with Fn1, which covers this particular case. Another case is Fn2 is overlapped with the Fn3. That is also possible. Okay, Fn2 is overlapping with Fn3. Similarly, if you look into Fn3, Fn3 is overlapping with Fn4. Okay, and Fn3 is overlapping with Fn2, which we have covered here. So if Fn2 is covered with Fn3, means Fn3 is also covered with Fn2. Right. Now, if you talked about Fn4, Fn4 is overlapping with Fn1, which we covered here. And Fn4 is overlapped with Fn3, which we have covered here. So these are the 4 situations which arises for this particular illustration. Okay. So let us see one by one. So I'll go for Fn1 and Fn2. So this is my Fn1 and this is my Fn2. Okay. So you can see there is 2 type of line. One is a solid line, another is a dotted line. Okay. So solid line is nothing but the current situation. Okay. and dotted line indicates that alternate situation. Alternate situation, right? So for example, in this case, you can see there is two vehicle. This particular vehicle, it is called this V1. This vehicle is V2. Okay. These two vehicles are in the overlap region of FN1 and FN2. Okay. These two vehicles are in the overlap region of FN1 and FN2. So, but currently, as I said, there is two line. One is solid line, another is dotted line. Solid line is currently they are getting service. So currently they are getting services 421 and 560. So before migration, number of resource block required is 516 plus 421. That is 937. Right? So this is your current situation I told you. But you have an alternate solution. You can go for dotted line. So what you will do? If you migrate, so instead of taking this 516 plus 421, if you decide to take 327 plus 315, I am writing here 315 plus 327. How many resource block is required? 642, right or not? How many resource block is required? 642. So you can see here there is a reduction, right? Before migration you need 937, but if I go for this alternate one, so number of resource block required is 642, right? Number of resource block required is 642. So obviously the number of resource block is reduced. How many resource blocks reduced? That is nothing but 937 minus 642. So you can say 295 resource blocks are reduced here. Okay, 295 resource blocks are reduced. Obviously, it is a better solution. This dotted line is better than the solid line, right or not? So like that, this we have done with the pair of formulas, right? That is FN1 and FN1 with FN2. So can you try with other fog nodes? As I said, you can try with FN1 with FN4. You can try FN2 with FN3. You can try FN3 with FN4. Can anybody try and tell? For example, I am telling the next one which I am going to do, that is FN1 and FN4. These two. This is FN1 and this is FN4. Can anybody tell what is the value you will get before migration and what is the value after migration and what is the reduction? Can anybody calculate? I am giving you 2 minutes time. Can you calculate? You write in the chat box. Yeah. One answer came, that is 942. I am expecting it is before. So let me write here 942. Then you calculate for after migration. Yeah. So after it is saying after migration, it is 625. Reduction is 317. Okay. So let me check. Let me do here. Okay. So let me solve this one, right? How many vehicles in the overlap region? So let me write this vehicle is vehicle 3 and vehicle 4. So you can see there is a solid line. it is showing 260. There is a dotted line. It is showing 213. And you can see there is a dotted line with the fog node. Let me write fog node 1. This is fog node 4. This is, I think, 412. And this line is 682. So yes, the first answer is correct, right? Obviously 682 plus 682 plus 260. So you will get 942, right? And after migration, we'll take the dotted line. So that is 213 plus 412. 213 plus 412, you will get 526, 625. Okay, and the number of reduction is, you have to subtract these two value, you will get 317. So thank you for sharing the answer. Okay, so this is the result we got, right, in the second situation. Now two migration we have done. You can see in the previous one, FN1 to FN2 migration we have done. We have reduced the number of resource blockers to 95, which we represent in the form of a graph. Then now we are doing FN1 with FN4, right? And number of reduction we are getting 317. We are writing in the form of a graph. Okay, now you understood, I think, what is the meaning of this edge. Now we'll proceed further. We'll migrate FN4 with FN3. So this is your FN4. This is your FN3. Okay. How many vehicles are there in overlap region? How many vehicles are there in overlap region? One, correct? One. So in the previous case, we have seen two, right? Previous both cases, we got two. So sometimes you may get 1, 2, 5 or whatever maybe. These are randoms, right? When you go for simulation, you don't know. So as there is only one vehicle, you can see currently it is 256. But if it is connected to FN4, the number of resource block required, it is 126. Obviously, 126 is a better solution than 256. So migration is accepted, and the number of resource block reduced is 130. That is 256 minus 126. Okay, so I am writing 130 here. Now you understood what is the meaning of this edge weight. Now, if I go for the last one, in which I am migrating FN2 with FN3. Okay, so like our last case, that is FN3, FN4, there is exactly one vehicle. Here also you can find exactly one vehicle, right? So before migration, we are getting here 486. After migration, it is 238. Before migration is 486. After migration, it is 238. So 486 minus 238. So that is, you will get 248. So this one is 248. Is it clear how to convert a network into a graph using maximum weight matching algorithm? We have not discussed maximum weight matching algorithm, but how you know how to convert it into a graph. Is it clear, or any doubt you can ask? Okay, I think it is clear. So now what we will do? So here you can see it is a graph, right? This is FN1, this is FN2, this is FN3, and this one is FN4. Okay, so let me write a bidirectional edge instead of writing two unidirectional. So we got the value is 317, 130, 248, and 295. Now, out of these, if you remember, we have a concept called minimum spanning tree. Which one we are choosing? The minimum one we are choosing, right? So out of these, which one is minimum? Minimum means the number of resource block reduction is less. Maximum means the maximum number of resource block is reduced. So which one will choose? Minimum one or maximum one? Which?
Maximum.
Will
Maximum block reduction.
yeah, we'll go for maximum, right? Because maximum resource block is reduced. 130 is the minimum resource block reduced between these two. Maximum resource block reduced is FN1 to FN4. So 317 is there. So the pair F1 and FN4 is selected first. Okay. So which one we are selecting? We are selecting this one first. Because it is the maximum weight. That's why this algorithm name is called as a maximum weight matching technique used in the DRO algorithm, that is dynamic resource orchestration algorithm. Right? But once you select this F1, N and FN4, as you are going for maximum weight, what is the next maximum weight? The next maximum weight is 295. In between FN1 to FN2. But this algorithm, this technique says that if you select a particular age, like I told you about spanning tree, so you have to ensure that there is no loop in that case. In this case, you have to assume that if you are choosing a pair of fog nodes, its adjacent edge should not be selected. This is based on this particular algorithm. So if you are selecting this particular edge, that is FN1, FN4, so FN4 to FN3 edge you cannot choose, FN1 to FN2 edge you cannot choose. Because it is connected to either FN4 or FN3. Those edges are connected to FN4 and FN1, you cannot choose that edge. You don't have any option. You have only one option to choose FN2 to FN3. The next selected pair is FN2 to FN3. So although you have calculated, finally the number of resource block reduction is 317 and 248. That is 565. So DRO is not considering the resource block reduction between whom? FN4 to FN3 and FN1 to FN2. But why we are calculating this one? The reason is that without calculation, how we will come to know which one is maximum weight? That's why we are calculating. But finally, we are selecting the pair of fog nodes which are not overlapping with each other. Okay. Like FN4, FN1 we are choosing is this adjacent edge we are not going to choose. Just like if you think something called as graph coloring problem in graph theory. Right? So in this way, actually, the DRO algorithm works. Right? So obviously, these two solutions you have not taken. That's why number of resource block reduction is quite less. So in order to avoid this one, people have come up with another algorithm that is called a signal aware algorithm. Okay, which is an improvement over DRO algorithm. Okay, so I'll tell the situation, what happened in the signal aware algorithm. But before that, we should know what is the main motivation of going for the signal aware algorithm. So in signal aware algorithm, we have two base stations. One is called as a macro base station, and another is called pico base station. So macro means large base station, pico means small base station. So in this case, if you see, this is one macro base station, and this is another macro base station, right? And there is some pico base stations. Here you can see this is a pico base station. There is also a pico base station. There is also a pico base station, like that. So there is a macro base station and there is a pico base station. Okay. So we consider a two-tier het net. Het net is called as HET stands for heterogeneous, NET stands for network. So we consider two tier. One tier, what we have? Macro base station. Another case, we have pico base station. So there is two macro base station and there is two traffic hotspot. This is called as traffic hotspot, where we have pico base stations. Okay. And each hotspot is having three pico base stations. I told you these are called as pico base stations. This big one is called as macro base stations, and this colored one is called as your hotspot. Overall, we call this is a two-tier net, heterogeneous network. So who is more powerful, macro base station or pico base station? Obviously, macro base station is powerful, right? And this UE is called as user equipment. Our mobile can be considered as a user equipment. Our iPad can be considered as a user equipment. So user equipment may be connected to the macro base station, or it can be connected to the pico base station. You can see in this diagram, these are the user equipments that are connected to pico base station. But these are the user equipment which are connected to the macro base station. It is the same as our IoT fog cloud. A device IoT can make a request to the fog layer. At the same time, a device can make also request to the cloud. Or a device can make a request to fog, which in turn request to the cloud. Okay, that is also possible. This is multiple tier. Here we are saying two tier, but it is a three-tier architecture. IoT devices can request to fog. Fog is incapable. Fog is forwarding that request to cloud. Or IoT devices assume that fog is not the solution, so it is a making the request to the cloud. Okay. So now let us see how to solve this problem, which I have introduced and solved in DRO algorithm, that you need to understand. Before that, I'll tell you how this macro base station and pico base station play an important role in the heterogeneous network. Now, here I am showing you a diagram which shows the time domain resource partitioning among the pico base station. So we have seen under a hotspot, we have multiple pico base station. Like you can see in the previous diagram, for the simplicity, we have seen there is 3 pico station under a hotspot. Okay, we have 2 hotspot, right? In each hotspot, we have 3 pico base station, right? Now, there is a concept that is called as ABS. ABS stands for almost blanking subframes. For example, you know macro base station, you know about pico base station. So macro base station is active for certain period of time, and after that period of time, it is giving chance to the pico base station and putting itself in a almost blanking subframe mode. What is the meaning? So here you can see there is 1 minus A and A. 1 minus A is a time duration. Okay, as we are considering time domain, it is a time duration in which both macro base station can work or pico base station can work. Okay, 1 minus A phase, macro base station can work, but first priority is given to macro base station. Then, if there is a scarcity of resources, pico base station can work. But when we have A phase, in this case, macro base station is put in silent mode. Okay, macro base station is periodically mutes or silent in the A phase. This A phase. That is called as almost blanking subframe to mitigate any kind of interference to some small cell users. Right? Always, if a high priority node is there, that is only going to execute. Low priority node may not get the chance to execute. So in order to avoid this one, there is a phase, that is A, where only pico station will work. So macro station base station is put in switch off mode. I hope you understood. This phase where macro base station and pico base station can work, this is the phase where a pico base station can work. Now, this A phase is again further divided into A1, A2, A3 up to AI. What is I? I is nothing but number of slices. So this macro ABS, almost blanking subframes, is now divided into L slices. Because in each and every hotspot, we have seen there are multiple pico stations. Each hotspot, we have seen multiple pico stations. They can distribute like pico station. One pico station can pick A1, another pico station can pick A2, another pico station can take A3. So with each slice, whether it is A1, A2, A3, or AI, a set of pico cells are allowed to solve users concurrently. Okay, and this phase is repeated. You can see 1 by A, 1 by A, again A, and it is repeated. Okay, now let us formalize. You can get more idea in this slide. Let us represent this problem into a graph. Okay, and graph coloring solution. For example, somebody has given an Indian map where it shows the boundary of each and every state, and somebody asked you to color the India map with in at a constant that no two consecutive states who shares the boundary, they should not be assigned with the same color. That is our graph coloring problem, right? For example, state 1 is assigned with red color. So its neighbor state is, let's say, 2 and 3. They should not be assigned with the same color. Right or not? Similarly, you can see 5 is another state or a node which is sharing boundary with 3, 2, 4, and 6. So it should not be assigned with the same color. But what is the restriction? The restriction is that you have to color the map or a graph with a minimum number of colors. Okay, minimum number of colors. Okay, now this phase is called as your 1 minus A. This phase is called as your A. So what I told you, in 1 minus A phase, I told you both macro station can work or pico station can work. But priority will be given to the macro base station. Right? You can see in 1 minus A zone, who is active? We have divided into number of frames. So this particular situation or set of frames, 1 minus A, that is both macro base station 1 and macro base station 2 are initially available up to 3 time slots. Time slot 1, 2, 3. Now from time slot 4, 5, 6, 7, 8, 9, 10. So here it is a 1 minus A phase is over. So this is our phase A, which we can divide into I number of slices. So the pico base station with the same color are assigned to same pico operating mode. For example, if you assign 1 with red color, you cannot assign 2 and 3, but you can assign 5 with red color. So 1 and 5 is assigned with red color. Similarly, if you assign green color to 2, 2 and 6 is not directly connected. They can be assigned with same color. Okay. Similarly, 3 and 4 can be assigned with the same color. All of you know, if you are a CS background person, you know what is the use of graph coloring problem. Simple problem is that you should not assign the same color to two consecutive nodes. So now, if you see this picture, 1 and 5, these are what? Pico base stations. So as they are assigned with same color, they can work in same pico operation mode. So you can see the frame 4 and 5. Okay, these two frames are given to pico 1, base station 1 and pico base station 5. Similarly, if you go for node number 2 and node number 6, okay, for example, they are given with the frame number 6. Okay, this one frame it is given to pico 2 and pico 6. It's based on the load, right? Whether you need 1 frame or you need 2 frame or you need 3 frame. Similarly, another one you can see, let's say the node 4 and node 3. they are assigned with the next two frames, that is frame number 7 and frame number 8. So there are 3 pico operation mode. What are they? The first one is 1 and 5. The next one is 2 and 6. The next one is 3 and 4. Okay. But in 9 and 10, what is 9 and 10? In 9 and 10, suppose there is a requirement. If requirement increases, what happens? All pico stations can work simultaneously. Okay. All pico stations, they can work simultaneously. So this part you can see, which we have seen in maximal weight matching algorithm. Right? 1 5 can make a pair, 2 6 can make a pair, and 3 4 can make a pair. So there are 3 PONs. That means 1 can migrate with if they are belongs to same pair. Okay, you can see these are the pairs, right? So 1 can migrate with 2, 1 can migrate with 3. Similarly, 5 can migrate with 6, 5 can migrate with 4, 5 can migrate with 3 also, and 5 can also migrate with 4. So it can migrate with anyone, right? So based on, because their reachability, you check the reachability. That is 1 is connected to 2 and 3, so it can do migration. But if you look into 5, 5 is connected to 2, 4, 6 and 3, and there belongs to different color. So they can migrate. That's why in the 5 case, you have a lot of options. Right? 5 can migrate with 2 or 3 or 4 or 6. But 1 can migrate only with 2 and 3. So with this motivation, they have developed the SA algorithm. So similarly, I can generalize it by saying that 2 can migrate with whom? 1, 3, 4 and 5. 6 can migrate with, tell me, 6 can migrate with
5 and 4.
5 and 4. Right? Now you understood what is the use of this algorithm. Right? So PM that allows all pico base station to active simultaneously is selected at 1, 2, 3, 4, 5, 6. Which one? This one. In this case, you have seen POM that allows all pico stations to work at a time. When load is more, the all will work. Okay. So in order to avoid the conflict, we have colored this one. Right? Pico 1 with Pico 5, Pico 2 with Pico 6, and Pico 3 with Pico 4. Okay. Now come back to our problem, which we discussed using DRO. So what we have seen here? In the previous one, we have seen we have taken FN1 with FN1 with FN3. Okay. Okay, you can make a pair. Like if you take, let me write here, FN1, FN4, FN3, FN2. So if you put graph coloring problem. So what is the pair? If FN is assigned with, let's say, red color, so you cannot assign red color to FN4 and FN4. So we have to make FN3 is one red color. Similarly, FN4 is assigned with green color. So FN2 is assigned with red color. So FN1 is migrating with can migrate with FN3. FN2 can be migrated with FN4. Right? So let us choose one pair. That is, I am taking FN1 from here, FN2 from here. Right? So you know in the previous calculation, if I take FN1 and FN4, there is 2 vehicle. So it is coming 682 plus 260. Right? If I take vehicle 1, vehicle 2, it is 260 and 213. So it is solid line. It is dotted line. Similarly, if you go for FN1, this is FN4. So this one is dotted line and this one is solid line. So here it is 682, it is 412. Okay. So in this case, before migration, it is 682 plus 260. Before migration, with FN1 to FN4, sorry, FN1 to FN4 if you do, here I am doing FN1 with FN2. Okay, anyhow, in this situation you can see, okay, or let us complete this part. When you go for FN1 with FN2, right? So the solid line is 516 plus 421, so it is 937, and dotted line indicates 315 plus 327, so it is 642. The number of resource block reduced is 295. Okay, so I forgot, in the previous case we have taken FN1 to FN4. First we need to take FN1 to FN2. You can take anything, there is no issue. Okay, after that what you will do? See the an interesting situation here. FN1 with I am taking FN1 with FN4. This case the reduction is same as DRO algorithm. If you remember, DRO case also we got the same result. But when you take FN1 to FN4, you can see in the chat box the result is written. It is 682 plus 260, right? So before migration it is 942. After migration we are getting 213 plus 412, which is 625. The number of resource block reduction is 317. That we have calculated in DRO case. Now see the interesting thing. So if V2 is earlier connected to 682, or it is consuming 682 number of resource blocks, now it is reduced to 213 if you take a dotted line. But what about this one? Earlier it is taking 260, right or not? Earlier it is taking 260, but now if you take dotted line, it is increasing to 412, right or not? So we are not going to migrate in the case of vehicle V1. V1 case will retain our old solution, and V2 case will update to our new solution. So let me repeat the same thing in this slide so that you can understand more clearly. Look into these two vehicles. Okay. So solid line is 260. Here solid line is 682. So if you go for dotted line, 682 is reduced to 213. Obviously it is a good solution. But here solid line is 260. Dotted line is 412. Is it a good solution? Increasing 260 is increased to 412. Is it a good solution? Yes or no?
No.
It is not a good solution. So we are not going to do migration here. So if you are retaining the old solution, and here I am updating to the new solution, the number of resource block reduction is number of resource block required is 260 plus 213. That is 473. What is my existing solution? My existing solution is 260 plus 682. 942. So 942 is now reduced to 473. So number of resource block reduced is 942 minus 470, that is 469. So this is the improved solution in the case of SA. That's why SA is performing better than the previous algorithm, that is DR. Right? This is the only situation.
Sir, I have one doubt.
Yeah, please, madam.
Sir, here what we are trying to do is same vehicle 1 and vehicle 2 are utilizing the FN fog node 4 resources. Won't be that too much load on fog node 4? Because
No, if
previous.
correct, but your question is a nice question. So you're saying 260 and 213 now is after migration. Let's say this is vehicle B1, this is vehicle B2. Both are now after migration is under FN4.
Yes, sir.
Right? But in early solution, one is under FN1, another is under FN4,
FN4.
right?
Yes, sir. So now it will increase the workload on fog node 4 where FN1 will be idle, right?
I did. So why we are doing this one? Because we need to accommodate to the upcoming vehicles, right? If you save some resource block in current iterations, that will help you when you go for the real-time simulation in which new vehicles are arriving in the network. At least at that time, FN1 can get FN1 is available with more resource block. That can be helpful. Otherwise, if you go for this, let's say in the previous solution, I think we have 213 plus 412 in the case of DRO. So it is 6 to 5. Okay. I think in the previous case it is 6 to 25. In this case, you see, now I'm giving a solution of 473. Earlier solution is 625. We are wasting around 150 number of resource blocks. Right. That is also one of the issue. Obviously, it is going to increase the load on FN4, but later point of time, if FN4 is overloaded, let's say more vehicles reach to FN4. So at that time, we'll see the updated number of resource blocks and we can migrate from FN4 to FN1 again. But in order to accommodate upcoming vehicles, 473 is the best solution because we reduced the number of resource blocks, more than 150 resource blocks we have reduced in comparison to the DRO.
Okay, sir. Thank you.
Yeah. Anyhow, in this, we are taking a static situation here. So your question is really valid question. But when you take real-time simulation, you will come to know saving the resource block by migrating between two different fog nodes. Although both vehicles are assigning to the same fog node, that is also a better solution. But race situation, if you see the performance of DRO is same as the SA situation. For example, if you go for FN3 with, let's say, FN2. So we have only one vehicle, that is 486 is the currently serving, 238 is the alternate solution. So if we migrate, the number of blocks, resource blocks reduced is 486 minus 238. Okay, so number of resource block reduced is 248. So the solution is same as the DRO, there is no other change. Similarly, when you take fog node 3 with fog node 4, there is only one vehicle. So 256 is current. After migration, it is 126. So the number of resource block reduced is 130. So now, what we will do? So we have taken two pair. One is FN1, FN3 is a pair because they are not neighbor of each other. FN2, FN4 is another pair because they are not neighbor of each other. So now, if you do, let's say, first fog node of pair 2, okay, that is FN2. And if you want to migrate with FN1, earlier we have migrated with FN1 with FN2. You can do FN2 to FN1, but you will get no improvement. Whatever migration is happened between FN1 to FN2, it is symmetric. That is FN2 to FN1 is also same thing. So you will not get any migration successful. Even if you do also, if you make a loop and do it in through code, you will get the same solution. Similarly, you try with FN3 with FN2, FN3 with FN4, also you will get the same thing. But we are not trying FN3 with FN4 because they are neighboring of each other. Okay. So there is no need to do it because if you represent in the form of matrix, if you take a lower triangular matrix, there is no need to take the upper parts. Right? It will not improve your result. That is the reason why the migration is not takes place between FN2 to FN1 and FN2 to FN3. So overall, if you compare, like here you can see again we are trying with FN4 to FN1, FN4 to FN3. So once one sort of migration is done, as we are taking a static situation, definitely or snapshot of a particular situation, the migration is not beneficial. Even if you do, it will simply run, but there is no improvement. Okay, so how many resource blocks we have reduced here? First case it is 295, second case it is 469, which is different from our previous algorithm DRO, then 248 and 130. So total we have reduced is 1142. So in the previous case, DRO case, if you remember, we took the maximum one, that is 317, and we took 248. Right? 317 plus 248. So the number of resource block reduced is 565. Because in that case, we have taken, if you are choosing a particular maximum weight, you should not choose its neighbor. Like if I selected FN4 and FN1 edge, I should not select these two edge. Right? That's why the performance is not that much improved. But in this case, we are trying for each pair of fog nodes, right? Only the load of FN1 can be shared with FN3, and the load of FN4 can be shared with FN2. Okay, means they can jointly work together. That's why we are making pairs. But they can exchange the things, right? Like FN1 can exchange the thing with FN4 or FN2. So that's why if you see here, the result is same, but in the second case, we have improved a little bit. And FN1, FN2 case, here we have not taken. But in SA algorithm, we are considering that one. So the number of resource block reduction is 1142. So it is almost twice than the DRO algorithm for this typical situation. Okay, so now we'll go for another algorithm that is a combination of DRO and SA algorithm, which we call it DRO plus SA. So DRO plus SA algorithm is very simple. First, you are going to apply DRO. Okay. Next, we are going to apply SA algorithm. So you know how to apply DRO algorithm. Once you get the result of DRO, then you apply the SA algorithm. So obviously, in this situation, if you apply, you will get the result similar to SA algorithm. But if you take a different typical situation, you can see DRO case you will get different result, SA case you will get different, DRO SA case also you will get different result. Okay, let us understand how actually it works. So when you take the fog node 1 and fog node 2, these two fog node, right? When we take these two fog nodes, so before migration, obviously it is 516 plus 421, so it is 937. After migration, it is 315 plus 327 as per the DRO algorithm, right or not? So, so in this case, what we can say, the number of resource block required is 937, right? But we are taking 327 instead of 516, 315 instead of 421. Both case we are improving in the case of SA. So DRO case also it says that you choose the alternate one. SA case it says that select the minimum one. So both case we are getting after migration, it is 315 plus 327. So the number of resource block reduction is 937 minus 642, that is 295. Okay. So try to understand two phase you are applying. First is DRO algorithm. So I can say 516 and 327, 315 plus 421. This is your current one. What we will do in DRO algorithm, just we exchange. We will choose the alternate one. So it will come 315 and 327 in DRO algorithm. But what we will get in SA algorithm, SA says that you can do 516 to 327, 421 to 315. Subjected to it is minimum. It is the current one. So 516 to 327, it is accepted because it is reducing. 421 to 351, it is accepted as it is reducing. Okay. That is individual one. When you go for DRO plus SA, what we are saying, once you get the result of DRO, that is 516 plus is 516 and 327 and 315 and 421. Your current situation after DRO is 315 and 327. So if you go for alternate one, 327, 516, it is increasing. 315 to 421, it is also increasing. So we are not improving the result by the help of SA algorithm. Is it clear? So number of resource block reduction. Okay. So number of resource block reduction in this case is 315. We reached to 315 plus 327. So number of resource block reduction is 295. So note that DRO case also 295, SA case also 295, DRO plus SA case also it is 295. Okay. Now come to this situation. You can understand in this slide how these three algorithms works. So I am migrating between FN4 to FN4, FN1 to FN4. So 260 and 412. Okay, one side. Another side 213, 682. And current solution is 682 and 260. What is the result in DRO? Can anybody say? We'll choose the alternate one, right? So it is 412 and 213. Right or not? 412 and 213. So you will get total is 412 plus 213, 625. Okay. The number of resource block reduction is how many resource blocks you have reduced here? How many resource blocks you have reduced here? 260 to 412, there is no reduction. Right. 680 to 213, there is a reduction. So number of resource block reduced is 469. Right? That we have seen in DRO algorithm. But what SA says? You take 260, 412, 213, 682. 682 to 260 is your current solution. So what we are doing? 682 to 213. It is minimizing the it is reducing the number of resource blocks. So we are accepting it. 260 to 412, it is increasing. So we are not accepting it. So we are choosing these two. How many resource block reduced? 260 is as it is 260. 680 to 213, it is 469. The number of resource block reduced is 469. But when you go for DRO SA, what is the result of DRO? DRO result says that you take 260, 213, 412, 682. Okay. So DRO has changed 682 solution to 213. Okay. Again, it has changed the result to 412. Right. It is choosing the alternate one, right? That's why it is taking 412. But SA says that 412 you have to again move to 260 because that is minimum one. That's why it is coming 260 plus 213. So here the number of resource block reduced is 682 minus 213. That is 469. That is up to DRO. But when you apply DRO SA, right, 260 plus 213 is the solution in DRO SA. The number of resource block reduced is 412 is initially, now it is reduced to 260. This one. The number of resource block reduced is 152. So total number of resource block reduced is 469 plus 152, that is 621. I am repeating again because you may confuse here. So initially the solution is 682 and 260. DRO says that choose the alternate one. That is 412 and 213. Okay, that is the solution. But how much we have reduced? We have reduced 682 to 213. But we have not reduced to 260 to 412. We have increased. That's why we are not going to consider. Right or not? So that's why number of resource block reduction, if you see in this case, it is 469. Alternatively, SA, if you apply individually, it is selecting 260 and 213. So again, number of resource block reduced is, if you see initially from initial 260 is 260, there is no improvement. 682 213, there is a improvement. So it is 469. But once you get this solution up to this, you will apply SA. That is called as DRO plus SA. So the solution says that you have to choose 412 plus 213. 213 cannot be moved to 682, it is increasing, but 216 will move to 260. 412 is going to move to 260. So here there is a reduction. The number of reduction is 152. So this 469 plus 152 is reduced. That is 621. But overall, we reduced how much? This 469 only. Right. But if by doing these two steps, we have reduced the number of resource blocks 469 here. Again, we have reduced the resource block here by 152. Totally 621. That's why this DRO plus SA algorithm is a better algorithm in comparison to DRO algorithm and SA algorithm. Is it clear? Or if you have any doubt, you can ask. Overall reduction is same, but phase-wise reduction is increased. Is there any doubt? Okay. If there is no doubt, we will proceed to the next step. In the next step, we are migrating between FN4 to FN3. FN4 to FN3, we have only one vehicle. So 256 is the current one, and it is reduced to 126. So number of resource block reduction is 130. So the reduction 130 is also we achieved in DRO. We have achieved in SA, also in DRO plus SA. There is no improvement. All algorithm, apply any algorithm, you will get 130 only for this particular situation. Similarly, when you apply DRO plus SA to the pair of fog nodes, that is FN2 and FN3, this is your FN2 and this one is FN3. So there is a vehicle. So number of resource block currently it is serving is 486, but it can be changed to 238. So 486 minus 238, you will get 248, which is same as DRO, same as SA, and DRO plus SA case, we are also getting the same result. So in this typical example, which case we need to more focus? We need to focus only these two fog nodes, FN1 and FN4. Okay, FN1 and FN4. These two fog nodes we need to primarily emphasize. Okay. Now I'm comparing. Before comparing, I'm calculating total resource block reduction. It is 295 as it is, 248 as it is, 130 as it is. So you can see here 295, 248, 130. But in this case, only SA has improved and DRO plus SA also improved. We got better result in DRO in comparison, better result in SA. Also, we got better result in DRO plus SA. So number of resource block reduction, it is 1294. So if you compare the three algorithm, you can see the interesting case is FN1 with the FN4. Okay, FN4, FN1 with FN4. You can see initially it is 317, increased to 469, increased to 621. Other cases you can see the same value. Here you can see the same value. Here you can see the same value, same value. So if you understand this case, then you can distinguish DRO plus SA plus DRO SA. So there is another algorithm that is called as RO, which we call as random algorithm, which says that the fog nodes can get the vehicle or vehicles are connected to the fog node randomly. If V1 has a choice of FN1 and FN2, we'll generate a random number. Let's say the random number is 2. So I'm assigning to fog node. If the random number is 1, we are assigning to FN1. Okay. So the assignment of vehicle to fog node is random in the case of random algorithm. Because sometimes we have to compare with baseline algorithm. Baseline algorithms, you can say first come, first serve. Okay, which vehicle, the vehicle which entered first is going to be sort first. That is one case. Okay. Another case you can say round robin. Okay. Another case is round robin. So we will assign the task in some particular order. That also we can do. Okay. Another case you can say, let's say shortest job or something like that, or a random algorithm. Like that, sometimes we compare with the baseline algorithm. That's why we have also taken arrow into our picture. Okay. So now I will show you what algorithm we have developed as a part of our contribution. So the algorithm proposed as a part of our research work by one of my research scholar, that is the dynamic resource management algorithm, that is called as DRM algorithm. So in this case, I have shown a different network which we have taken, and it is also given in the research article. So you can go through the research article if you want to know more details. So we have taken here same 10 vehicles, right? We have taken 10 vehicles, but you can see only I think 6 vehicles are in the overlap region. We are not considering non-overlap region. For example, you can see this is your vehicle V1, vehicle V2, vehicle V6, V3, V4, V5. Only these 6 vehicles are available in overlap region. And how many fog nodes are there? There are 4 fog nodes are there. FN1, FN2, FN3, and FN4. Okay, FN1, FN2, FN3, and FN4. So now we are representing this vehicle to the fog node in terms of a matrix. Okay, like if you see vehicle number 1, it is in the coverage range of FN1 as well as FN4, and the number of resource block required is 292 here, and number of resource block required here is 433. Similarly, if you go for vehicle number 2, number of resource block required for first vehicle, it is 551. Number of resource block connected to FN4 is 209. Right? Similarly, if you go for B3, this is your B3. So here it is 328, here it is 288. Right? So now, if you see this orange color box, right? I have represented in orange color. I filled with orange color. What it indicates? It is the currently solved by that many resource blocks are solved to the vehicles by the fog node. So obviously it is 551 plus 531. That means fog node 1 is serving vehicle 2 and vehicle 4. The number of occupied resource block is 1082. Similarly, case of FN2 is providing services to B3. So it is 328. FN3 is providing services to vehicle V6. So it is 374. FN4 is providing services to vehicle V1 and vehicle V5. So number of resource block consumed is 633. Okay, just I have added this yellow orange color box. That is the current situation, right? Now we'll apply this DRM algorithm. What DRM algorithm says? It is passing one by one fog node and selecting the minimum. For example, before applying DRM algorithm, the sum of occupied resource block is 2417. 2417. Okay. Now, if you take FN1, you take fog node 1. Fog node 1, if I take in fog node 1 is reachable to only 3 vehicles. You can see, if you go to fog node 1, fog node 1 can provide services to only three vehicles. What are the vehicles? That is vehicle V1 it can provide, or vehicle V2 it can provide, or it can provide services to V4 also. Okay, fog node 1 is sharing boundary with FN4. Fog node 1 is also sharing boundary with Fn2. Right? So these are the three values. But what are the alternatives? So instead of fog node 1, fog node 4 can also serve vehicle B1. Instead of fog node 4, fog node 1 can serve B2. So if I take only fog node 1, this is the situation in which you can see minimum one is, out of all values, the minimum one is 209. So we have selected vehicle V2 first and we assign to fog node 4. And we require the number of resource block is 209. Okay. Now, if you go for vehicle V4, V4 has only two options, right? That is, vehicle V4 has two options. One is, if you see here, one is Fn1, another is Fn2, right? But out of which, if you see after eliminating this B2, which one is minimum in the matrix? It is 223. So V4 is assigned to the fog node 2 and the number of resource block required is 223. Now V4 is eliminated. If you talk about now V1, V1 has two situations. It can be assigned to Fn1 or Fn4, right? But Fn4 is already taken by V2. And if you take also Fn4, it is quite more in comparison to 292. So we have assigned to which one? V1 is assigned to fog node 1. So that is 292. So number of occupied resource block after first iteration, it is 292 plus 223 plus 209. Okay. Now, once the first iteration is over, you can see in this first iteration, V1, V2, V4. Let me write here. V1, V2, V4. They have got services. Okay, they got services. So now what you will do? There is a vehicle V3 and there is a vehicle V5 and V6 is also there. So I am going for Fn2. So Fn2 case, you have vehicle 3, vehicle 4 and vehicle 5. But out of that, vehicle 4 is already served. So we have to eliminate it. So I represent in different color. A number of occupied resource block, if you see in the previous case, okay, if you see in the previous case, it is 292, 223 and 209. So here it is 292, 223 and 209. So when you are choosing a minimum one, you should add with these values. For example, after eliminating B4, B3, B5 is are the options. So which out of which one is minimum? The minimum is 200. But already we have given the resource blocks 209. So it is actually 409. This is 200, not 200. It is 409 because 209 resource block already given to one particular vehicle. So excluding this one, if you choose, the maximum value is, here you are getting 278 plus 223. Here also you have given 223 resource block in the previous iteration. So the minimum one you will get is only 288. That's why B3 is assigned to fog node 3. And once B3 is assigned, you have only one vehicle B5. Okay, so B5 case, it is assigned to fog node 4. So it is now after end of second iteration, it is 292 plus 223, 288 and 409. Okay. Now in this iteration, B3 and B5 got service. That means earlier B1, B2, B4 is serviced, got services in first round, iteration 1. B3, B5 got services in the iteration 2. Now you left with only one vehicle, I think, that is B6. So if you go for fog node 3, B3, B6 is the only option. Right or not? So B3 is already assigned. So B6 is only left. So you have 374 and 123. We have 374 and 123. So what is the number of resource block occupied here after the end of this one? It is 288 and 409. So let me write here 288, 409. So although it is less, this 409 you need to add with 123. So it is 532. But in this case, it is 288 plus 374, which is quite more. So obviously, 123 plus 123 plus 409 is better in comparison to 374 plus 288. That's why B6 is assigned to fog node 4. So number of resource block reduced in this case, it is number of occupied resource block is now what 335. If you sum these values, 292, 223, 288, and 532, you will get, I think you will get 3, then okay, so you will get 1335. So before migration, the number of occupied resource block is 2417. After migration, the number of resource block is 1335. So we got a reduction of 44.76%. Okay, so DRO algorithm is better in comparison to DRO. If you solve the same problem using DRO, also using SA, then DRO followed by SA, which is DRO SA, and random algorithm, you will find DRM algorithm is better in comparison to other algorithms. Okay, so the what process we have adopted here? So DRM identifies the vehicles that are present in the overlapped region of the pair of fog nodes, and it determines the number of resource blocks allotted to those vehicles from the fog nodes. Then what it does? It migrates the allocated resource blocks vehicles between fog nodes in order to reduce the occupied resource blocks of the fog nodes. These are the two things which we have seen in the previous example. Now coming to the algorithm, if you look into the algorithm, what is our input? Our input is a set of fog nodes, and we are given with a graph G, which is VE, set of vertex and set of edges. And what is your output? Output is an optimal set of vehicles for resource block migration. Resource block migration is important. That is our primary objective. But we also evaluate this algorithm in terms of other 5 parameters. That is service capability, serviceability, availability, throughput, and resource utilization. So what I did here, I have taken a for loop where I have taken f number of fog nodes. So this loop will run for start from first fog node up to f number of fog nodes. Then we have taken PT. PT is nothing but the number of vehicles that are available in the overlapped coverage region. Then we calculate currently occupied resource blocks of ith fog node at time slot t. Because whenever we are assigning calculating the occupied resource block, sometimes already some vehicle is taking some resource blocks. That also we need to consider. That's why how many resource block is occupied currently, that also you need to calculate. Okay, that's why this loop is running from k is equal to 0 to PTI. That is nothing but a set of vehicles served by ith fog node at time slot t. A fog node is serving multiple vehicles, right? So that's why we need to calculate all the resource blocks that is consumed by that particular fog node before assigning to that particular fog node. And RBIK is the number of resource block allocated to ith fog node to kth vehicle. Then in this particular loop, if you see, there is 2 for loop. What we are doing for each neighbor of fog node, every fog node has some neighbor. So we find PT of ij. What is that? That is nothing but how many vehicles are available in the overlapped coverage area. Only after that you can do migration, right? That's why we are calculating, we are putting in a particular set, and we are calculating the number of resource blocks. If you put a resource block as a restriction, then you need to also check that you are not exceeding the number of resource blocks. Okay. And after this particular process, we apply a procedure that is called as migrate resource blocks. This is another procedure. Once you return from this particular procedure, and if you iterate this one with respect to f number of fog nodes, then after migration is successful or unsuccessful, you can calculate what is the service capability, serviceability, availability, throughput, and resource utilization efficiency. Now this is the migrate function which I have called. So migrate function is called when PT is not equal to 5. PT is equal to 5 means in the overlapped coverage region, in the overlap region, there is no vehicle is there. Then if there is no vehicle available in that particular region, then we need not call migration. If there is any alternative is there, then only you can go for migration. So this procedure also called another procedure that is called as find mean vehicle. That we need to find the vehicle with the minimum number of resource blocks. So if K mean not solved by F, and this ART of F, which is called as available resource block of Fth fog node at time slot T, which is greater than the resource block of Fk min, then only you have to migrate the resource block to the vehicles from a particular node I to another node, fog node F. Then once you've done the migration, you have to update the remaining resource block and occupied capacity of Fth and ith fog node. But if it is not solved, then skip the vehicle for migration. Even if you call the migration case, if this particular condition is not satisfied, we skip that particular vehicle for resource block migration. Okay. And finally, in the overlapped area, if there are multiple vehicles are there, you have to exclude that vehicle because you have successfully compared that one. Similarly, this is the procedure for find minimum vehicles. So we call this procedure to find the vehicles with minimum number of resource blocks. So I'm not going in detail of this particular process. Now, when you go for simulation parameters, you can find a lot of parameters are considered for doing simulation. So we created a virtual environment using the very well-known programming language Python. We used PyCharm IDE to implement this algorithm, where we consider the number of fog nodes is 10 to 50. We create different situation. In different situation, we have different number of fog nodes, but the number of fog nodes ranges from 10 to 50. So we consider mean arrival rate and mean departure rate. So mean arrival rate, you can see that is considered as a lambda, and mean departure rate is mu. So we consider only one situation by assuming that lambda is greater than the mu. Okay, but you can consider the cases which I discussed earlier, that lambda is equal to mu and lambda can be less than the mu. So mean arrival rate we have taken as here 10 vehicles per second. Mean departure rate we have taken 5 vehicles per second. And number of vehicles with respect to one simulation we have taken 2100. So per simulation we consider 2100 number of vehicles to get the results. And the network area which we have considered is 1000 M to 1000 M. The radio communication range of single hub communication is 100 meter. Single hub communication means between vehicle to fog node, it is a single hub communication. And bandwidth of fog node we have taken 10, 15, 20 megahertz to make it more realistic. Coverage radius of a fog node is considered 100 meter, means every fog node is having a range of 100 meter. If a vehicle is outside 100 meter of a fog node, so it is not reachable. And cumulative number of service connections, we have considered 2100 number of connections because number of vehicles is 2100. And required data rate, we have taken 0.5 to 2 Mbps, where 0.5 is the minimum data rate. And we generated the values in this particular range. So every vehicle has a desired requirement, but the minimum requirement is 0.5 Mbps. Time slot duration, we have taken 1 second. And confidence interval or simulation duration, we have taken 210 seconds. So with these parameters and their values, we have simulated and we have compared in the 5 different performance metrics. So I'm showing you 2 metrics here in this slide. One is service capability in percentage. Okay. So it is actually 20%. This one is 40%. This one is 60%. So you can see the service capability case, our objective is to maximize the service capability. So if you compare, the DRM algorithm is slightly better in comparison to other algorithm. And in this case, DRO algorithm performs poorly. And even if you compare the DRO with RO algorithm, random algorithm performs better than the DRO algorithm. That is the observation which we have made with respect to network service capability. Similarly, if you go for serviceability, again you can see DRM algorithm is in the first and DRO algorithm is at the end. Even if RO algorithm is performing better, which we have observed in the previous metrics, serviceability case also we observed that RO is better than the DRO. Okay, DRO is performed very poorly. Okay, so this is also considered in the percentage, not in 0.2 means it is 20%. And x-axis represent the time slot in seconds. So as I told, we have taken 2 10 seconds. Right, confidence interval or simulation duration we have taken 10 seconds. That's why x-axis represent these 2 10 seconds. Every second we have make some observations. Now you can see the result in another 2 performance metrics. That is, one is availability, another is throughput. Availability case, you can see DRO algorithm performs better in comparison to the proposed algorithm also. Right? It performs initially better up to around 150 time slots, but after 150 time slots, it is performing poorly because at that time the number of vehicles entering to the network increases, and the DRM algorithm performs better in comparison to DRO algorithm after 150 time slot. But availability wise, you can see RO algorithm performs very poorly. Okay, random algorithm performs poorly in comparison to all other algorithms. Similarly, if you go for throughput is drastically increased in the case of the proposed algorithm, and the poor performance is seen in RO algorithm up to around 120 time slot, and after 120 time slot, we have seen the DRO algorithm is performing poorly. But irrespective of the situation, initially DRO performs better for few time slots, that let's say 50 time slot. After that, you can see DRM performance is better. Coming to another set of performance metrics, we have also compared with resource utilization efficiency and resource block reductions. And resource block, in case of resource utilization, you can see we have make the visualization in the form of box plot, where we are showing the minimum value, first quartile, that is 25%, median, that is second quartile, then quartile 3, that is 75%, and the maximum value. Okay, so you can see the spread of the DRM algorithm is better in comparison to all other algorithms. It also shows that even if more vehicles are going to reach in further time slots, let it be after 210 time slots, DRM algorithm can accommodate it in comparison to other algorithms. And if you look into the resource block reduction also, resource block reduction case also, you can see DRM algorithm performs better up to, you can see we have taken observation up to more than 2000 vehicles, that is 2100 vehicles. In every situations we have seen our algorithm is better than the existing algorithms. So in these 2 talks, what we have summarized, what we have seen, that I will summarize here. So we have discussed 2 different problems in IoT, cloud and fog environment. And we have seen the essential, although I have not told you much about 5G network, but also you can see the communication is important with respect to 5G, right? How faster you have to communicate, that depends upon the network, right? So 5G can provide the faster communication between vehicle to the roadside unit. So we have discussed two algorithms in the first problem. One is RBSM and RRS. So we found that RBSM is better than the RRS algorithm. Then we discussed another problem in which we have seen 5 algorithms, in fact, that is DRO, SA, and DRO SA, and RO and DRM algorithm. And we have seen that DRM algorithm is better in comparison to DRO, SA, and DRO, SA, and RO. Coming to the simulation perspective, you can simulate, although we simulated in Python by writing a simple code, but you can also do the real-time simulation by taking simulation of urban mobility, that is SUMO, or NS2 or NS3. So our objective is to reduce the number of resource block reductions, but this work can further be expanded. Also, we have looking into the solutions where energy consumption can be minimized of the fog node, because not only resource block reduction is important, but also we need to focus on energy consumption. We need to minimize the energy, because if fog nodes are placed in different places, if there is no power source, so in that case we have to see that energy should be utilized properly. But it is quite challenging for these problems to get real-time data sets. There is no real-time data sets. You have, just like you have seen, I have shown you set of parameters and their values, in which we have taken certain ranges to generate our data sets. But if a real-time data set you will get, then it's better to evaluate the algorithm, but such data sets is not available with respect to this problem. So the first work, which I told you, RBSM, it is published in 17th International Conference on Distributed Computing and Information Technology. That is the 5th paper. That is in LNCS Springer. It is one of the good conference in our country. And the second work, DRM, is published in peer-to-peer network and applications. And some of the relevant works is published in Computer Material Continua, that is Tech Science Press, Journal of Ambient Intelligence and Humanized Computing, and also in IEEE Transition on Intelligent Transportation System. So you can refer these works. So these are some of the references. If anybody is interested to work, so you can refer these papers, and you try to, like I told you about, if you remember, two-tier head net, that is SA algorithm, you can find here. Okay, dynamic orchestration algorithm also you can find, I think, in this paper, the last paper, DRO algorithm. Okay, and also you can see this paper talks about MIMO HATNet, which is published in IEEE Transaction Communications. So you can go through these papers if you are interested. Yeah, thank you everyone. If you have any question, you can ask.